In this video, we'll talk about the greatest common factor and least common multiple, and then apply it to a few word problems. Let's begin with the definition of greatest common factor. The greatest common factor of a group of natural numbers is the largest natural number that is a factor to all the numbers in the group. To find the GCF, we've got a few steps. Step 1 is to write the prime factorization of each number. And we saw the prime factorization in an earlier video, though we will review it here as well. Next, you would choose all primes that are common to all the factorizations. And then, within these factorizations, we know that we raise those prime numbers to different exponents, so we would raise that to the least exponent. So, for the greatest common factor, you find the primes common to all the factorizations, and then you kind of do the opposite of what you might expect. You choose the least exponent. So greatest common factor chooses the least exponent. And then you form a product of all the numbers that you found in step 2, so you just multiply them all together. And the resulting product is your greatest common factor. So in this example, we will find the greatest common factor of 54 and 108, and we'll follow these 3 steps. For step 1, we are going to find the prime factorization of each number. So separately, I'm going to think about, well, what is the prime factorization of 54? Now, 54 is an even number, so we know it's divisible by 2. 54 divided by 2 is 27. 27, if we remember 3 times 9 is 27, we'll know is the same as 3 times 9. Now, I don't have to continue branching out 2 because it's a prime number, nor do we have to keep branching out 3 because it's also a prime number. However, 9 is not a prime number, and it could be written as 3 times 3. And the way that you know that you're done with this factor tree is that every ending part of the tree is a prime number, which you could refer to your prime number list. So the prime factorization of 54 could be written as 54 equals, we've got 2 occurring one time, so just 2, times, looking, we then have the factor, prime factor 3 that occurs 3 times. So 3 occurs, how many times does it occur? 3, so we're going to cube that. Next, we do a similar process to find the prime factorization of 108. 108 we know is even, so it can be divided by 2. Checking this in our calculator, 108 divided by 2 is 54. Now 54 is also an even number, it ends in an even number, so we could just divide that by 2. And we could write 54 as 2 times 27. Now again, these 2 branches are now prime numbers, so they don't have to be simplified further, but 27 could be broken down into 9 times 3, or 3 times 9. 3 is a prime number, doesn't need to be broken down further, but 9 does, 3 times 3. So then we would write its prime factorization, 108 is equal to, we see the prime 2 occurs at the ends twice, 2 because that's the prime number, square it because it occurs twice, times, this is multiplication. Then we see 3 occurs 3 times. So we write the prime number 3, and then we cube it because it occurs 3 times in the factorization. And a way that you can know if your work is correct, so for instance for 54, 2 times 3 times 3 times 3 is 54, so 2 times 3 cubed is 54. For 108, 2 times 2 times 3 times 3 times 3 is 108. So we know these are the correct prime factorizations. We're done with step 1. Now for step 2 of this process, it says choose all primes common. So looking at this prime factorization, I see that 2 is a common prime, and we see that 3 is a common prime number. But we see that they have different exponents, so we know it's going to involve the GCF 54 and 108 is going to involve 2 times 3, but to what exponents? Okay. How do we know what exponents occur? It's the least exponent that it has in any of the factorizations. So here you would combine piece by piece. So just looking at 2 for right now. The exponent in 108's 2 is squared. And since there's no exponent written here for the prime factorization of 54, that's an implied 1 is the exponent. So here, the least of the 2 exponents that occur for 2 is 1. So you could either write this as 2 to the first power, or since 2 to the first power is just 2, you could write it without an exponent. Okay, continuing this, we would then say we're going to compare the exponents on the next factor, 3. Both of these 3's have exponent 3, so the least between these is also 3, so this will be 3 cubed. And that would be the prime factorization, the greatest common factor of 54 and 108 based on their prime factorization. And that would complete our answer with step 3. Now we're asked the same question, but now with a different pair of numbers that still find the greatest common factor, which you might see abbreviated as GCF. Step 1 will be to find the prime factorization of 360 and the prime factorization of 2700 separately by making your factor tree. Then you're going to pick all the primes that are common to both factorizations, picking the least exponent that appears in any factorization, multiplying that together as the GCF. I recommend you pause the video now and then reference the notes that we just did earlier to get your answer to this. Unpause to check your work. Now 360 is an even number, so we know it could be divided by 2, so I could write out the prime factorization as 2 and 180. 2 is a prime number, no more is needed there, but 180 could be factored further. It's also prime, so we could divide that by 2. 2 and 90. Prime is good, no more is needed, but 90 could be split up in here. 90 is a prime number, so I could also say divide it by 2, it's an even number. So 2 times 45. Now I know since 45 ends in a 5, it's divisible by 5. So I could divide that by 5 and say it's 5 times 9. 5 is a prime number, so no more simplification is needed, but 9 could be split as 3 and 3. And the way you know that you're done is the end of each of the branches of the diagram are all prime numbers. So the prime factorization of 360, we would count how many times does each prime factor occur. 2 occurs 3 times, so we would say 2, and then it occurs 3 times, that would be our exponent 3, and then we write our multiplication dot. Next, I see numerically we've got 2 prime factors that are 3. So 3 occurs how many times? 2 times. Next, we've got the single prime factor of 5, and it only occurs 1 time, so you could either write it as just 5 or 5 to the first, but generally we don't write the exponent to the 1, it's just implied. And the reason that we didn't do any of these as part of the prime factorization is they're not prime numbers, and also see that they got split off more and more. They weren't the endpoints of this factor tree. So that's the prime factorization of 360. You can multiply it together to check. Next, we find the prime factorization of 2700. Okay. Now, one thing to note is you could just keep dividing it by 2 because it's even, but that's going to take a bit of time. Sometimes it's more helpful to think about what would be the largest number that I know goes into this. And since it's got these 2 zeros here, I know that if I divided it by 100, 100 is a factor of 2700. So I could start by saying this could be split into 27 times 100. And now neither of these are prime numbers, so I'm going to have 2 splits. Now 100 is even, so I could divide it by 2, but that could take a bit of time. Again, there's many different ways you could write out the factor tree. There is one unique prime factorization. So instead, maybe we could do 10 times 10 is 100. Now 10 has 2 prime factors, 2 and 5, which we would repeat for both branches of 10. So this portion of the factor tree is completed because notice we kept going through until we got down to only prime numbers at the end. But we do still need to split apart the 27. We know 27 can be written as 3 times 9. 3 is prime, so nothing more is needed, but 9 could be split in 3 times 3. Now this factor tree might look different than yours, but you'll see we'd still get the same prime factorization. So we decide how many prime factors do we see. We list them out in order if possible. We've got 2 as a prime factor twice here. 2 squared times, next we see that there's 3's as prime factors, and they occur 3 times. So we've got 3 cubed times, we've got 5 occurring twice. So we'd say times 5. How many times does it occur? 2. And notice if you actually multiply all that out, 2 squared times 3 cubed times 5 squared, you do indeed get 2,700. So you can always check your work with these problems as you go. Now with the prime factorizations, and I'm actually going to write these next to each other. With these prime factorizations, it can be helpful to write them lined up in order with the prime factors. And what we'll do here is we know that for the greatest common factor, it's got to include only those primes that are common to each factorization raised to the least exponent that ever occurs. So in this case, we see that it's both factorizations have 2, 3, and 5 as common prime numbers. So we can just write out 2 times 3 times 5, but then we still have to figure out each of their individual exponents. The way you figure out the individual exponents is you look at the 2 different parts of the prime factors, so 2 cubed, 2 squared, and you choose the least exponent that ever occurs in any of the factorizations, so that would be 2 squared. Moving next to the 3 prime factors, we've got a 3 squared and a 3 cubed. Notice the square occurs to the least, so this would be also 3 squared. Continuing, we would see that we've got 5 here. Now we've got an exponent that's not written, which is always an implied 1, versus 5 squared. 1 is the smallest, so you could either write that as 5 to the first, or just not write the exponent because it's implied to be to the first power. So the greatest common factor is this number, and if we were curious about what number this is, we could type it into our calculator. 2 times 2 for 2 squared, times 3 for 3 squared, times 5. So the greatest common factor of these two numbers is 180. So the value is 180, and this is its prime factorization. So we've got the same instructions for this problem. Find the greatest common factor. The main difference is now we've got 3 different numbers to compare. And in both of these, we're going to make our factor tree and write out their prime factorizations. And then we're just going to choose all the common prime numbers to the least exponent possible. So I recommend that you take a moment to pause the video just to review prime factorization and do the factor tree and write out the prime factorization for these 3 numbers, and then unpause to check your work. So possible factor trees for 720, 1000, and 1800 are written here. Now, depending on how you chose to start your factor tree, yours might look different, but our prime factorization should still be the same because the intermediate values might be different based on how you're dividing them, but you'd still end up with the same prime factors at the end. So for 720, we see that we've got 4 times. So that's 2 to the 4th times, we've got 3 twice, 3 squared, times, and we've got 5 once. That's all of the factors or prime factors that we've got for 720. You can multiply them together to check your work. For 1000, the prime factorization is 2 occurs 1, 2, 3 times, 2 cubed, times 5 occurs 3 times, so we've got 5 cubed. And then for 1800, we've got that 2 occurs 1, 2, 3 times, 2 cubed, times 3, which occurs twice, so we've got 3 squared, times, now 5 occurs twice, 5 squared. So these are our prime factorizations. Let's now go to step 2. So at this point, I think it could be helpful to rewrite the numbers and their prime factorizations just vertically so that we can easily compare what primes are common to each factorization. For instance, see that we've got the prime 3 in the prime factorization of 720 and 3 in the prime factorization of 1800, but it's not present in 1000. Because it's not present in all the prime factorizations, it's not going to be a part of the GCF. Not 3. However, we see that 2 occurs in every prime factorization and 5 occurs in every prime factorization. So we will have 2 times 5. Now all that's left to determine is to what exponents. And here we just look at them piece at a time, and remember we're going to choose the least exponent that occurs for any of the factorizations. So looking at all of the 2's that are in the prime factorization, we see that we've got an exponent 4, 3, and 3. The smallest of these is 3, so 2 will be cubed. Next we look at the 5. Okay, we've got a 5 with an implied exponent 1, a 5 with an exponent 3, and 2 we're going to choose the least. So we're going to write this as 5 to the first, or remember that is implied, you could just leave it as 5, because 5 to the first is 5. So our greatest common factor, if we wanted to know the numerical value of that, that would be 2 times 2 times 2. So we've done 2 cubed times 5. So 40 is the greatest common factor of 720, 1000, 1800 altogether. The last concept that we're going to cover in this section of notes is that of least common multiple, which we abbreviate as LCM. So if we've got a group of natural numbers, then the smallest natural number that is a multiple of all the numbers in the group is the least common multiple. And these are the steps to find the LCM. I recommend writing it down on your note sheet. First, you write the prime factorization of each number. So we see that this first step is the same as the first step for GCF. They both begin with a factor tree and finding the prime factorization. Where they deviate is in step 2. So here we choose all primes, and here's the key thing, that belong to any factorization. In the GCF version, you had to pick only the common primes. But here it says if there's a prime occurring in any factorization, choose it for the LCM. And then how do you know what exponent to raise it to? You raise it to the exponent or power that is the greatest exponent that occurs in any of the factorizations. Multiplying all these prime numbers with the appropriate exponent together gives you the least common multiple. So it's kind of switched. For the greatest common factor, you choose the least exponent that occurs to all the common primes. But for the LCM, you choose the greatest exponent that occurs on any of the primes in any of the factorizations. We'll begin this by looking at the least common multiple of 135 and 280, following these steps. So step 1 is the same as before. We need to make the factor tree of these and find their prime factorization. I know 135 is a multiple of 5. I could use my calculator to divide that just to see what it is, and it goes in 27 times. 27 is 3 times 9. Again, these don't have to be simplified further because they're already prime numbers, but 9 could be split in 3 times 3, which tells me 135 is equal to the smallest prime number is 3, and it occurs 3 times. 3 because that's the prime number that occurs, cubed because it occurs 3 times, times. We have the prime number 5 that occurs only 1 time in this factorization, and then you could check 3 times 3 times 3 times 5 is indeed 135. Next, we would find the prime factorization of 280. 280 is an even number, so we know it's divisible by 2. That's 140, which is also even, so it's divisible by 2 as well. 2 is prime, so it doesn't need to be simplified further. That's 70. 70 is also prime, so it could be divided by 2. 35. Now 35 is a multiple of 5. Specifically, if we divide this by 5, we see that it's 7 times 5 is 35. And now we've gotten down to the end of the branches of all of the factor trees, our prime numbers. So we just have to write the prime factorization. So 280 is, we see that 2 occurs 3 times, so we'd write 2 cubed. 5 occurs once, so times 5 to the first, implied first exponent. 7 occurs once. And now I'm going to write down the prime factorization for 135 below this just so I can easily compare them. And we're going to be looking at steps 2 and 3 of the least common multiple. Now for the least common multiple, we are looking for any primes that occur in any factorization. So for instance, 2 occurs in the prime factorization of 280, but it doesn't occur in 135, but that doesn't matter. It occurs in one of them. We don't yet know the exponent. 3 occurs in one of the prime factorizations. Even though it doesn't occur here, for the LCM, that's fine, so we write down 3, not sure of the exponent yet. 5 occurs in both, but the key is it occurs in at least one, so we write that down, wait for the exponent, same with 7. Okay, so now that we know these are the prime numbers that are part of the least common multiples prime factorization, we go piece at a time and write down the exponent, and looking at the instructions before, you choose the greatest exponent that occurred in any of the factorizations. So starting with 2, we see 2 only occurred in this factorization. So the greatest possible exponent is cubed because that was the only exponent that ever occurred on a 2 in either factorization, so we'd write this as 2 cubed. Let's increase numerically. Next, we would look at 3. Now 3 only occurred in this factorization, so again, it's kind of told to us your exponent on the 3 would then be cubed because that is the greatest because it's the only one. Next, we'll move to 5. Now 5 occurs here, and they're actually to the same exponent implied 1, so we either don't write it or you could write the 1 as the exponent. And then finally, 7 only occurs here, again to the first power, so we could have the implied first exponent. So this is the prime factorization of the LCM, and let's multiply them to figure out exactly what this would be numerically. So 2 cubed is 8, so that would be 8 times 3 cubed is 27 times 5 times 7. So the least common multiple is 7,560. And what that means is 7,560 is the smallest number that is both divisible by 280 and 135. Because, for instance, 270 is divisible by 135. It divides imperfectly twice, but 270 is definitely not divisible by 280. So that's the idea of the least common multiple. So next we've got a similar example. The main difference is though we're dealing with smaller numbers than before, we now have 3 numbers where we're finding their least common multiple. To begin, you would write the factor trees and prime factorizations for these 3 numbers. I recommend you do that and then pause the video, unpause to check your work. So we would get the factor trees. One possible factor tree is this. Now, the prime factorization for 12 from any factor tree, we see that we've got the prime 2 occurring twice. So that'd be 2 squared times, it also has the prime number 3 occurring once, so times 3. Next, we'd write the prime factorization for 18. So here we've got 2 occurring once, times here we've got 3 squared because it occurs 2 times. Next, we write the prime factorization for 60. 2 occurs twice. 3 occurs once. And then 5 occurs once as well. So these are prime factorizations for 12, 18, and 60 individually. To find the least common multiple, we choose all primes common to any factorization, and then we know the exponent we should use is the greatest exponent that occurs for that prime number in any of the factorizations. So just looking at the primes that occur in any of the factorizations, we see we've got the prime 2, the prime 3, and the prime 5. So it's 2 to something times 3 to something times 5 to something, and then we'll just go one at a time to decide which exponent is there. Looking at all the occurrences of 2 in the prime factorizations, we are choosing for the least common multiple the greatest exponent, which would be squared, because this is an implied 1. So both of these are the same value, so we'd have 2 squared. Now next we look at the 3 in the prime factorizations. The greatest exponent that occurs is squared as well, so this will be 3 squared. Now there's only one factorization that includes 5, and it's implied to the first power, so this would just be 5 to the first as well. That's the greatest exponent that occurs. So this is our least common multiple, And let's decipher what this value is. 2 times 2 times 3 times 3. That gets the 2 squared, the 3 squared, times 5. 180 is this least common multiple of these 3 digits. Now we just went through the process of how to find the LCM by finding the prime factorizations and then choosing any prime number that occurs there to the greatest exponent that ever occurs. So that process works perfectly. This is an alternative method. Use it if you prefer it. If you don't prefer it, just use the original method. So if you've got two numbers, L and M and N, you could find the LCM by multiplying the two numbers and then dividing by their greatest common factor. Note that this method only works for two numbers and it can't find the LCM of more than two numbers. So we're going to use this formula to find the LCM of 77 and 84. One reason this is particularly helpful is if you already know the GCF of the two numbers. So to answer this problem using this formula, step 1 will be to find the GCF of 77 and 84. After we have that value, we would then use this formula to say that you multiply 77 times 84 and then just divide by the GCF that we already found in step 1. So the GCF of 77 and 84, we would probably want to use our factor tree method. We're going to write out the prime factorization, choose all the primes that are common to both factorizations, and then use the least exponent possible, following the 3 steps listed in the beginning of this lesson. Now we've gone through some examples of how to find the GCF. If you want, you could pause the video and find it yourself. I'm listing out the factor tree that I found for 77 is 7 times 11. The factor tree ends there because both of these are prime. 84 has one possible factor tree of 2 times 42. Splitting the 42, 7 times 6. 7 is a prime, so it doesn't need to be split further. 6, 2 times 3. And these would yield the factorizations of 7 times 11 for 77. 2 squared, because there's two 2's, times 3 times 7 for 84. And we know the GCF says that you've got to only have primes that are common to both factorizations. And the only prime number that occurs in both factorizations is this prime value of 7. And then the rule says choose the least exponent possible, which these both have an implied 1. That would be our least value. So the greatest common factor of these two numbers is 7. Completing the formula to find the LCM, we would use the formula above that says multiply the two numbers in your calculator and then divide by that greatest common factor. So we'll have 77 times 84, and then we're going to divide that number by 7. And we get the least common multiple is 924 using this method. You also could have written out the factor trees of 77 and 84, chosen all prime numbers that occur, and then picking the greatest exponent possible. Our final two examples from this section involve word problems, where from the word problem, we need to identify if they're asking us for the greatest common factor or the least common multiple. I'll read this first example. Joshua has 450 football cards and 840 baseball cards. He wants to place them in stacks on a table so that, and here are our details, each stack has the same number of cards and no stack has different types of cards within it. So for instance, I couldn't have in one stack 5 football cards and 5 baseball cards. I've got to have, for instance, 10 football cards, 10 baseball cards. So they can't mix, and we also want each stack to be equal. So we couldn't have stacks of different heights. They've all got to have the exact same number, and we can't mix different types of cards together. What is the greatest number of cards that he can have in a stack? So the way to think about this problem is we've got a few constraints. First of all, we want to know what is the greatest number of cards that he can have in each stack. So for instance, you couldn't say, well, 450 is even and 840 is even. So you could just have these 2 card stacks. Okay, in this case, we would need 450 divided by 2. We would have 225 2 card stacks of football cards. And for the baseball cards, 840 divided by 2 is 420. So we would have 420 of 2 card stacks of baseball cards. But this does not work because it doesn't include the greatest number of cards that could be in each stack. For instance, this is just we've got 2 cards together, but there could be a greater common factor between 450 and 840 than 2. So this is an example of something that doesn't fit this last part of the criteria. So not only do we need to be able to divide the group of 450 and 840 into the same number, but we've got to divide it into the same number that is the greatest that we could compare for both of them. So this is asking us about the greatest common factor. If we knew the greatest common factor between 450 and 840, then that would be exactly the right number of cards that we could put in each stack, such that no stack has different types of cards within it because it's perfectly divisible by each number, and it would be the greatest such number because it is the greatest common factor. There's no factor that divides into both categories evenly that is greater than that. So at this point, once we've determined that this word problem is asking us to find the greatest common factor, we would just set about finding the GCF of 450 and 840, and once we've done this, we are done with the problem. Now, we have discussed the greatest common factor a few times so far. Just for additional practice, I recommend you would pause the video to find the GCF, finish the problem on your own, unpause to see the solution. To find the greatest common factor, we first do a factor tree to find the prime factorizations. Now, 45, I know if I multiply 45 times 10, that would get me 450. And again, I could have also divided 450 by 2. That would just be a longer factor tree. Now, both of these are not prime numbers, so they're both going to need to be split further. 10 is 2 times 5. We're done here because we've gotten down to 2 prime numbers at the end. 45 is the same as 5 times 9. 5 is good because it's a prime number. 9 still needs to be split. So we would have the prime factorization is 2 occurs once, so we would just write 2 times. We see that 3 occurs 2 times. 3 squared times 5 occurs 2 times, so that would be 5 squared. Next we find the factor tree and prime factorization of 840. This is the same as 84 times 10. You could also divide it by 2. It would get the same prime factorization, just slightly differently. We know 10 can be split into 2 and 5 in its factor tree. And then 84, if I'm not sure, it is even, so I could divide by 2. And we get 42. 42 is the same as 6 times 7. 7 is prime, so it doesn't need to be split. 6 needs to be split further to 2 times 3. So the prime factorization of 84, we see 2 occurs 3 times, so that would be 2 cubed times 3 occurs 1 time, times, we see that 5 occurs once, and then finally 7 occurs once as well. So if I write the prime factorizations near each other just so I can view it, I would get 450 as this. And we get this now with greatest common factor. That's what we're looking for. Remember, greatest common factor, you've got to have the prime numbers that are common to both factorization. For instance, we see that 2 is common to both factorization, as is 3, as is 5, but notice 840 has 7 as a prime factor, but 450 does not. So 7 is not going to be a part of our greatest common factor. So we know it's going to be of the form 2 times something, 2 to some exponent times 3 to some exponent times 5 to some exponent. For greatest common factor, we look at the 2 in both prime factorizations, and we choose the least exponent possible. So greatest common factor chooses the least exponent, The least exponent here is the implied 1 exponent, so that would be 2 to the first power. Next, we would look here at 3. We've got an implied exponent of 1 and a 2. We choose the least exponent possible, so we would choose just 3 to the first. Next, we're looking at our prime factors 5. Again, we've got a square and a first power. We choose the least one, so that would just be 5 to the first power. So the greatest common factor is 2 times 3 times 5, which is representing the number 30. So the greatest common factor is 30. So what that means is if we've got stacks that are 30 high, then we would have each stack having the same number of cards. No cards would have to be mixed with others to keep that stack 30 high, and we would have the greatest number of possible stacks. Or sorry, the greatest number of cards in each stack. That would be the correct wording of this. Okay, this is our last example for this section. Terry has some pieces of 2x4 lumber. Some are 60 inches long and others are 72 inches long. All of the lumber must be sawed into shorter pieces. If all the sawed pieces must be the same length, what is the longest such piece such that no lumber is left over? So we don't want any leftover remnants, and let's assume here that sawing the lumber doesn't shorten the board. So this is not a realistic assumption, but it will make our problem easier so we don't lose any lumber by cutting it. So we want all the cut pieces to be the same length, and we want to make sure that we can use the largest pieces as possible. So we've got two different situations. We need to cut boards that are 72 inches long, and we need to cut boards that are 60 inches long, and we want the resulting cut to be the same length and nothing left over. And we want that to be the largest such way. So for instance, I couldn't cut the 72-inch board into a 70-inch board and a 2-inch board because they wouldn't be the same length. There's like a 2-inch scrap. We couldn't do that. So we want to think about what this problem is really asking us. We've got two different numbers, and we want to be able to divide them because cutting the 60-inch piece of lumber into different pieces of equal size is basically dividing the board into equal length pieces. To help us visualize this a bit, if I cut the 60-inch board into two pieces, it would be two 30-inch pieces. And if I cut the 72-inch board into two pieces, it would be 36 inches each. So nothing's left over, but the issue is that the boards are not the same length anymore because I would have ending results of 36 inches and 30 inches. So even if we can divide the boards into different length pieces, we want to find the greatest possibility where we've got the greatest length of each of the individual pieces such that all the pieces together can mix together. You don't know that you've got one of a different size and one of another. And that would be the idea of the greatest common factor. So if we can find the greatest common factor of 60 and 72, then that's going to be the size of resulting board length. That would be the largest such that we have nothing left over, and that would be the same size that we could cut from each of the different length boards and get our required result. So this problem will be determined if we can find the GCF of 60 and of 72. So I recommend you take a moment and work through these two problems, pause the video, unpause to check your work. And we're finding the GCF of these two numbers. 60 has a factor tree 2 times 30. 30 can be split into 2 times 15. 15 can be split into 3 times 5. So we would have 2 squared times 3 times 5 as our prime factorization for 60. 72 has the prime factorization 2 and 36. 36 is 6 times 6, which can be split into 2 times 3, 2 times 3. So we've got 2 occurs 3 times, so 2 cubed times 3 occurs twice, 3 squared. I'm going to write these near each other so that I can visualize what's going on. Now for greatest common factor, what we're looking for here, you choose only those prime numbers that are common to both factorizations. So for instance, 2 is common, 3 is common, but notice 5 is not common. So our GCF will involve a 2 to some power times a 3 to some power, but 5 will not be part of that factorization. Next, we determine the exponents. You look at the exponents on 2 and you choose the least exponent possible in the factorizations. So we've got a 2 squared and a 2 cubed. We're going to go with 2 squared. Then we've got the factorization of 3. We see we've got 3 to the implied first power and 3 to the second power. For greatest common factor, you choose the least. So that would be to the first power. And remember, you don't have to write to the first power, it is implied. This would be the number 2 times 2 times 3. 12 is the greatest common factor, and this is its prime factorization, 2 squared times 3. With this, we know that if we cut the 60-inch boards into 12 pieces, 60 divided by 12 is 5, so we would have 5 little cuts, each of 12 inches each. And then we'd have the 72-inch board, and 72 is divided by 12 exactly 6 times, so we would have 6 cuts of exactly 12 inches each. And if we cut each length of board 12 inches, then we see the result would all be the largest possible length, such that we could get an equal amount from each of the different size boards. So that's it for this section on least common multiple and greatest common factor. If you have questions, definitely send me a message through Canvas and I'll be happy to answer them. I recommend you look at the homework problems in preparation for the quiz. Thank you.